We've all heard that classic phrase, right? The living fossil. It gets thrown around all the time when people talk about sharks. But welcome to this explainer, because today we are going to dive into some incredibly fascinating, hard data that completely flips that narrative right on its head. We're unpacking the shark evolution paradox to find out if they really are just ancient relics or actually the ultimate dynamic adapters.
Okay, just think about this time scale for a second, because it's honestly staggering. We are talking about a group of animals that's been navigating our oceans for roughly 450 million years. To put that into perspective for you, sharks were around before trees even existed on land, literally, older than trees. They've survived multiple mass extinctions, they watched the dinosaurs rise and entirely fall, and they've outlived countless other species. It's a survival streak that is just kind of hard to fully wrap your head around.
But, this immense survival streak naturally begs a really fascinating question, and it's the core of what we're exploring today. Did sharks just, hit the biological jackpot early on, find this perfect generalist form, and then just become static living fossils? Like, did evolution just look at them and say, yep, my work here is done? For the longest time, that was actually the underlying assumption. But as we're going to see, the fossil record and some cutting-edge biomechanical analysis tell a completely different story.
To really crack this mystery, let's time travel back about 370 million years to the Devonian period. We're zooming in on a specific case study from an amazing fossil deposit called the Cleveland Shale, looking at a highly successful early shark known as cladosalach. This predator grew up to 6 feet long and prowled the ancient oceans of North America. And, thanks to some pretty incredible geological luck, paleontologists have uncovered dozens of exquisitely preserved specimens. They're so well preserved we can even see traces of muscle fibers and internal organs.
Now, what absolutely blows my mind here is how many unshark-like traits this ancient predator had. It was so far apart from the sharks we know today. Unlike modern sharks, cladosalach was almost entirely scaleless, save for a few right around the mouth, eyes, and fins. It also completely lacked claspers. Those are the structures modern sharks use for internal fertilization. So how it reproduced is still a total mystery to us. And get this. Instead of a mouth tucked safely under the head, it had a terminal mouth right at the front of a short, rounded snout.
These bizarre traits brilliantly illustrate just how vastly different ancient mechanics were compared to the apex predators we see today. Cladosalach actually had a jaw that was fused directly to its cranium, and the jaw joints themselves were surprisingly weak. But evolution is clever, right? It compensated for that weakness with massive, highly powerful jaw-closing muscles. The teeth were multicusped and smooth-edged, perfect for grabbing and holding on for dear life, but entirely useless for the tearing and chewing we associate with, say, a modern great white.
So if you can't chew your food, what do? Well, you adopt a totally different strategy. Brilliantly preserved stomach contents show us that it used pure, unadulterated speed to hunt small ray-finned fishes, swallowing them completely whole, tail first, right on the run. Paleontologists actually studied 53 separate specimens with preserved gut contents and found the prey intact and facing forward. That proves cladosalach was this active, high-speed pursuit predator just chasing down meals from behind. And honestly, it needed that breakneck speed because it was sharing the water with Dunkleosteus, a 20-foot-long armored monster that would have happily made a snack out of it.
So how on earth did shark jaws evolve from that rigid, fused, non-chewing structure to the incredibly diverse, flexible jaws of today? To answer that, we have to zoom out to a groundbreaking study by a team of researchers using a concept called theoretical morphospace. Basically, think of this like a video game character creation screen, but for real-world biology. Instead of only looking at jaw shapes that exist right now, scientists mathematically mapped out every single possible jaw shape a shark could theoretically have.
Just look at this map. It charts out hundreds of theoretical and actual jaw shapes across 400 million years of evolution. The researchers took 2D outlines from 122 living species and 95 extinct ones, spanning across 35 different orders, and they generated this massive grid of 513 theoretical shapes. Some of the shapes out on the far edges are actually biologically impossible, like the jaw would literally intersect itself. But mapping the whole shebang gives us a perfect canvas to see exactly where real sharks fall on the spectrum of physical possibility.
Now, here is where things get super fascinating. Every single shape in that space was subjected to digital stress tests to measure one absolute critical biomechanical trade-off. Basically, you can either snap your jaw shut incredibly fast, or you can withstand massive bone-crushing bite forces, but you can very rarely do both perfectly. A slender, curved jaw is lightning fast for snatching slippery prey, but it will shatter if you try to crush a shell. On the flip side, a thick, robust jaw can output immense crushing force, but you totally sacrifice that split-second closure speed. So, let's overlay actual real-world shark species onto this mathematical landscape. See those darker blue areas? Those represent maximum efficiency. That dark blue is what we call the Pareto front, the absolute optimal mathematical balance between speed and strength. Now, if sharks were really just stagnant living fossils, you'd expect them to have found this dark blue peak of perfection early on and just, sat there chilling for 450 million years, right?
But boom, the data shows the exact opposite. It's a huge evolutionary twist. Early sharks essentially started at peak efficiency for generalist hunting, right in the sweet spot of that optimal trade-off. But as millions of years ticked by, they actually evolved away from this optimal center. The jaws of modern sharks and rays have trended toward much more robust shapes that, strictly mathematically speaking, are less optimal for that pure speed versus strength balance.
So why? Why would evolution push an animal away from peak biomechanical efficiency? One word: ecology. They didn't lose their edge, they specialized. Habitat and diet drove them to develop highly robust jaws tailored for very specific needs. For instance, lots of groups evolved thick jaws specifically to crush hard-shelled prey, a lifestyle known as durophagy. Deep water species went off exploring wild, highly varied jaw shapes to survive extreme environments. Meanwhile, your top pelagic predators stayed a bit closer to those optimal efficiency peaks. Essentially, they traded generalist perfection for highly specialized ecological dominance.
As you can clearly see in the summary of this comprehensive study, this completely rewrites the book on sharks. It shatters the whole narrative of them being static relics of the past. The data definitively proves that the shark family tree is a story of continuous dynamic change. They didn't survive 450 million years by staying exactly the same. They survived by constantly adapting, experimenting with new jaw morphologies, and dominating newly available ecological niches.
I absolutely love this quote because it hits the nail right on the head and cements the core takeaway of our explainer today. Sharks are the ultimate dynamic adapters, constantly shifting their morphology to conquer new environments. From that stiff-jawed, fast-swimming Cladocelash of the Devonian period swallowing fish whole, all the way to the incredibly diverse array of bottom-feeding rays, deep-sea chimeras, and apex predatory sharks today, their history is defined by constant reinvention, absolutely not stagnation.
Which really leaves us with one massive lingering question. Having mastered the art of ecological specialization over hundreds of millions of years, what is the shark of the future going to look like? Because right now, our oceans are undergoing incredibly rapid shifts in temperature, chemistry, and prey availability. These ultimate evolutionary adapters are once again having their morphospace put to the test. Thank you so much for joining me for this explainer, and I really hope you never look at a shark as just a living fossil ever again.